Welcome back to our electronics course. In this lecture, we'll continue our journey with the linear particle accelerator, and we'll explain another type of accelerators called cyclotron. One big problem of the linear particle accelerator is that sometimes it's not practical to be implemented. Because, as you see here, we need always the distances between each two plates to be larger than the previous distance. So, for example, if we need very high speed for the particle, we may need thousands of these plates, and we may need also to implement them in very large distance, miles and miles. So sometimes linear particle accelerators is not practical to be implemented. One simple modification that may enhance the picture is that we can put some magnetic field here. So, instead of implementing the linear particle accelerator with plates just in one direction, we can make the journey of the electron in two directions. One trip in the positive x direction and another trip in negative x direction. The original picture is that these plates is also here. Now we will implement them just under these stages. What will happen is that the cathode will emit an electron. It will be accelerated by this plate. When it comes from this hole, the polarity will be changing, so it will be accelerated more using this plate, and so on. When it comes out from this plate, it will find a perpendicular magnetic field here, so it will move in a circle. After completing a half cycle of this circuit, its speed, instead of being in positive x direction, it will be totally reversed in the negative x direction. So it will move through this hole, will be accelerated by this plate, another acceleration between these two plates until it hits the target. So for example, if the original linear particle accelerator need to be implemented in 1 mile, now it can be implemented just in half a mile. Okay, let's ask us a question. Can we make this magnetic field here also to make another trip in positive x direction and increase more the velocity of the electron? The answer for sure is no. Because if we make the same here, after this electron to be get out from this plate, it will move around. But now to move from these two plates, the distance from these two plates must be larger than this distance. But as we see here, this distance apparently smaller than this distance. Okay. The question is still open. Can we make something better than the linear particle accelerator? Yes, we can. This is the cyclotron. A cyclotron is a small device. As you see here, it consists of two similar things. We call these things the D's, because if we look from above here, it's like the letter D in English. The letter D in English. If we look at 3D, it's just this D with some hole inside. Something like a sandwich. Okay. We will apply a square wave to these two D's like this, with a voltage VA and uniform half period of T. If the electron starts its journey from this point, assume at this moment there was a positive voltage here and a negative voltage on this D. So the electron will be accelerated toward this D. Inside this D, we have here a perpendicular magnetic field. So the electron will move in a circle, just like this, until it gets from this point, out of this D. At this point, the oscillator will be flipped. This will be a negative, and this D will be a positive, opposite than the previous situation. So the electron will be accelerated more toward this D. When it reaches this point, it will find also a perpendicular magnetic field, so it will go in a circle. But now the radius of this circle is higher than this one. And we will say why after a while. After completing this half cycle, the electron will be here. So we need to repeat this. So this will be flipped. This will return back to a positive, and this will be a negative. So the electron will be accelerated more. It will enter this D, move in a circle with a larger radius than this, and also than this, until it reaches this point, and we will continue with the same principle. At the last cycle, it will go with a very high speed toward the target. Okay. Why we are accelerating the electron? Is that because at each half cycle, the electron gains QVA. When it was here, it gains QVA. Q is the electron charge, and VA is the voltage between these two Ds. In a cycle, it gains 2 QVA. After one cycle, it gains the QVA in this strip, and another QVA in this strip. So after n cycles, the total energy of the electron is 2n QVA. So the speed at n cycle is Vn, and the kinetic energy is half the mass Vn squared. So Vn, which is the speed after n cycle, is equal to the square root of 4n QVA over n. So, now, why the radius is increasing after each half cycle? Simply because the radius is equal to the mass multiplied by the velocity over qb. We can get this equation from the lecture in which we explain the motion of the electron in a magnetic field. Okay. So as we see here, if we increase the velocity, the radius will be increased also. After n cycles, V will be Vn using this value, so Rn is equal to n over qb, 4n qva over n. As you see here, if n is 1, this will be 4 qva over n. If n is 2, it will be 8 here, so the radius is increasing. Okay. We say also that when the electron reaches this point, the polarity must be flipped. The positive must become negative, and the negative must become positive. Then after this half cycle, the same will be reversed. This negative must be positive, this positive must be negative, and so on. How we be sure that the oscillator will flip the polarity at the exact correct point, when the electron is at these points or at these points? Simply because the cyclic period time of electron inside the magnetic field is constant, whatever the speed by which the electron moves on this circular motion. If we go back to the lecture in which we explain the motion of the electron inside the magnetic field, we find that the periodic time, the time taken by the electron to complete a circle, is equal to 2 by m over qb, which is constant. So this time is half this time, tb over 2. This time taken from this point to this point is also tb over 2. This time taken from this point to this point is also tb over 2. This time taken from this point to this point, which is the largest distance traveled by the electron, is also tb over 2. We can say in other words, at this point, this is the lowest speed the electron has, but this is the lowest distance the electron moves. At this point, the electron increases in velocity, but its distance is also increases. So here, the velocity increases, but also the distance traveled by the electron is also increases. So this cancels this, and the time remains the same.